from the name, I think you can already guess the meaning, what we need to do. Yeah. Actually, it is a very useful algorithm, and it is used a lot in our, modern era, because we need to search a lot of information. Keywords-based search, think about that. Is this the fundamental algorithm for keywords-based search, right? Yeah, we use keywords-based search almost every day, right? Have you thought about how to do the keywords-based search the fastest way? Have you thought about it a little bit? Yeah. So here we have a chance to study that fundamental problem for information search. Yeah. But definitely here, the first time when we look at this problem, brute force one, right? Brute force. So definitely this one cannot be a very efficient one. Yeah, this one cannot be a very efficient one. Yeah, brute force. Yeah. But that is our starting point. Yeah. But later, after that, then we may like to consider better, faster, more advanced searching algorithm. Yeah. But that one, because extremely complicated. Yeah. It's in our textbook, extremely complicated. Yeah. I taught that once before, the student couldn't follow that. Too complicated. Yeah. Yeah. I'm thinking about that. So if I need to give you in this class, yeah, very challenging. Yeah. Yeah. Let me find the, good way about that. Yeah. Because some students may be curious about that advanced. Yeah. Although it's in the textbook. So if you are interested, you can read, you can study by yourself. But because it is too hard, too complicated, I may think, yes, at this point, I may like to think in this way. I do not talk about it in the regular lectures, because I believe at least 90% of you will get lost. So I may record a video outside our class, and I post it as optional supplementary reading. If you're interested, you just watch my video. Okay. If you're not interested, you just skip it. Yeah. That probably a better way for that advanced string searching algorithm. All right. Okay. Yeah. Let me start this one, very easy to follow. All right. Yeah. So let's look at this one first. Yeah. All right. Yeah. I try to, let me see. Time I have, because I need to go a little faster today. I try to complete my plan today. There are 3 topics. This is the first one. I try to complete it by 6 o'clock. Then starting from 6 o'clock, then we can do the new 2 new topics. Yeah. All right, so let me start. All right. First, I need to give you the problem description. Okay. Although you know the meaning, you can guess the meaning pretty close, but we need to represent it mathematically, precisely, so that we can, do a accurate solution. Yeah. All right, so let's start. The first topic I'd like to talk about, mathematical representation. Yeah. Sometimes when a problem is given, there is no mathematical representation for it. It's just a problem description using our natural language. Okay, but after that, in order to solve that problem, sometimes we need to write our own mathematical representation. So you may have a good mathematical representation or bad mathematical representation that would impact the solution. A bad one, so because for the same thing, you can use different ways, different formulas to represent the same fact, the same problem description. You can use many different ways to describe it, right? But sometimes if you can choose relatively better, relatively simpler, that would help a lot, because good representations can help you, help you streamline your thinking, make your thinking easier and smoother. Yeah. All right. Yeah. Let's start. Yeah. Our problem number 5, string matching problem. Yeah. The problem description: given a string of n characters, we call it text. Yeah. Because we will have 2 pieces of text. Yeah. The first one, that's the text body, or that text part. It's like a document. Yeah. The second piece of text, that's the, keywords. Yeah. Usually we mean the keywords. All right. So the second one, a string of n characters, we call a pattern. Yeah. Because in our discussion, when we refer to these 2 parts of text, we need to choose some terminologies. Yeah. Here, text and a pattern. Yeah. The number of characters in the pattern, m less than or equal to n. Yeah. All right. So the setup, this is the initial setup of the problem. All right. Now the question: find a substring of the text that matches the pattern. The meaning is clear. Okay. Yeah. So based on this description, I think you have no problem understanding what we need to do here. The next question is, how do we get started? The first step to get started, because from the given description sentences, it is not convenient for deep discussion, not convenient. Yeah. Because we don't have formulas, right? It's hard to manipulate the given data, right? If we don't have formulas, how can we manipulate the given data, right? It's hard, all right? We cannot, manipulate the sentences, given sentences, right? So we have to choose good, efficient, convenient mathematical representation. So that is our first step. Yeah. So let's look at how do we do it. All right. Yeah. All right. Yeah. Here, a little more explanation. Find its location, because what we need to be more specific about the solution. What do you mean you get a solution, right? So we need a specific meaning for our solution. That is the location of that substring. Location of a substring. you need to provide the location of the substring. But you may have another question. What is the location of a substring, right? A substring contains several characters. The location of which character is used for its location, right? You may have that kind of question. Yeah. All right, so here, the first character of the substring. Here, this location would mean the first character of the substring. Not the last one, not someone in the middle. Yeah, so that is clear. Okay? The first character of the substring. All right. Yeah, leftmost. Yeah, so here the text representation. The index I, yeah, but indexed I with respect to what string? Given text. Given text, the first character with index 0, 1, 2, 3, 4. Yeah, so here if we want to write more specific, the indices for the text from 0 through the last one is n-1. Okay, yeah. All right. But that is the case for the pattern is found in the given text, right? But you have a case, possible case, the pattern cannot be found in the given text, right? Yeah, that case, you need to include it. Yeah, we just return -1. How about that? Okay, a -1 means no matching as the solution. Yeah. All right, so with that, so now our first solution, straightforward brute force solution. Yeah. Yeah. Mathematical representation. Yeah. We want to represent the given data precisely. Location, characters, precisely. All right. All right. So then because we can apply appropriate mathematical tools. Now, all right, the text, let us use a sequence of characters. Now, here we use T variable, T variable with subscripts from 0 through n-1. Okay. Then the pattern P, a sequence of characters for pattern P variable with subscripts from 0 through n-1. Yeah, so, all right. Then requirement. Our, what should be the final solution? Yeah, we need that part, representation. Yeah. So let's look at the location. Yeah. If we find a solution, how do we arrange text sequence and pattern sequence and identify the substring that matches the given pattern? Yeah. So let's look at that. All right. For a matching, look at the first character that is matched. First character, we assume T sub I. T sub I equals P0. Okay. Yeah. Ti, the I, yeah, we know, yeah, in that range. Okay. Yeah. The range, we know that. Right. Yeah. Yeah. Well, yeah, probably, yeah, not that much, because when I close the end of the array, character array, we won't take that part, right? Yeah, but here roughly in that range, but we can still eliminate a few more index possibilities. Yeah, we will see that later. All right, so if the first character matches the first character in a substring, here we're talking about the substring, first character matches the first character of the pattern, then we should also match the following in order characters, with a general expression t sub I plus j. Here you can see we use many variables. Here, I is an integer variable, and the j is another integer variable. All right, I plus j location for the t sequence. All right, yeah, so that character equals p sub j, and so on, until we reach the end of the pattern string. That is, with precise expression, t sub I plus n minus 1 equals p sub n minus 1. You can see that's the accurate representation for the answer, for the solution case. Okay, all right, yeah. All right, after we write out all this kind of necessary details, next we can find a solution. Yeah, the strategy. Let's look at the strategy first. Yeah, guess and verify strategy. Yeah, I remember we applied this strategy before. Yeah. I have some impression we applied before, guess and verify. Yeah, but here, because in this class, we need to apply the strategy many, many times. So this is the second time we apply it. Yeah. All right, so thinking, so let's use a diagram. We try to, understand the problem visually. Yes, so many times we need to draw diagrams. Yeah. All right, but here, because this in our first solution, we try the brute force method, and the typical way in the brute force exhaust all the possibilities. That's the typical way. So here, a natural question is, can we exhaust all such m substrings in a given text? Yeah, given text. We know there are a finite number of characters, and each substring takes consecutive characters in the given sequence with length. The length of the substring is n. So we should have finite number of possible substrings to be considered. Yep. So theoretically, we can exhaust, right? Yeah. So the next question, how do we exhaust? Yeah. All right, so let us try, every time extract an m substring from the text with consecutive characters from beginning to end, from left to right. How about that? We scan the given text from left to right, character by character, position by position, in natural order, one after another. Pretty straightforward, all right? Pretty obvious. Yeah. every time when we look at one substring with length m, we do comparisons, compare it with the pattern for a possible match. Yeah, okay, yeah, pretty straightforward. Now let us answer the first question. How many m substrings do we need to do the comparison? Do we need to do the string comparison? Here, I like to describe it precisely, do the string comparison, because here we have two types of comparison. String comparisons and the character comparisons, right? Yeah, character comparison and the string comparisons. Two different meaning here. Yeah. Here, I'm asking you about how many string comparisons. Yeah. For m substrings. Yeah. All right. So we need to find that answer. Yeah. You can guess it. Can you make a guess based on intuition? Based on intuition. Yeah. Because in your mind, you can think of the, visually, you start with the first substring, leftmost. You start from the leftmost position. So you chop one m substring. Yeah. Do comparison. Or here we do not need to look at the comparison result. We just look at the substrings we have. Then you move one position to the right, another position to the right, and so on until you hit right end of the text. You stop. In that way, can you imagine how many m substrings we can chop down, we can extract from the given text, right? Yeah, just guess. Not necessarily precise. We just want to make our guess as close to the answer as possible. Okay, as close as possible. Because later we will do some adjustment to fix the difference. Now, if there is some error, we will fix it later. Yeah. All right. So the first guess, probably n minus n, right? Yeah, the length of the text string and number of characters, and the length of pattern and number of characters. Then you take the difference. That is n minus n, right? We don't know if this is an accurate guess or not, but we know it should be a close guess, right? Yeah, because visually in our mind, we imagine, the picture. Yeah, that's pretty much close to what we. Okay. All right. Carmen asked a question. Confused. Written formula. Oh yeah, that one. Why is it the t sub I plus j when I represents t's left r and j? All good. Yeah, good question. Yeah. All right. Yeah, just go ahead. When you have such question, just ask me. All right. Yeah, actually, this part a little confusing. For most students, or at least for many students, a little confusing. Yeah. So Carmen asked me, yeah, when we let's look at this part. Yeah, this is the general expression part. Carmen asked me why at the left-hand side, the subscript is I plus j, and right-hand side, the subscript is j, right? Yes. Yeah, so let me answer in this way, all right? Let's look at the starting point. Let's look at starting point. What is our starting point? T sub I equals P0, right? Yeah, all right. What is the next one? Yeah, we just try a few examples. We will find the rule. Okay, yeah. The second one, T sequence, we should move one character to the right. That position should be I plus 1, right? And P, we need to move one character position to the right. So that is P1, right? Yeah. Consecutive characters. All right, yeah. How about the next location? T I plus 2 should be equal to P sub 2, and so on, right? Yeah, look at that. So you can see when T plus 1, P side, we just take that 1. We ignore that I part, right? When T plus 2 at P side, we just ignore that I, so we put 2 there, right? Similarly, when we move multiple characters, left-hand side, we have I plus J, and right-hand side, P sub J. Can you see the pattern? Can you see the rule? We just ignore the I part, right? At the P side, the subscript for P, we just ignore the subscript of T side, ignore that I, all right? Yeah. So, you know, from the rule, when we do the experiment, we find that rule. How about that? Okay, yeah. And you can treat, yeah, so there are many ways you can explain, you know, this kind of relationship, yeah. So P, yeah, look at that. Let me use another way to explain it. All right, the starting point of P, of T comparison, starting point at I position, all right? Starting point for P, 0 position. I corresponds to, yeah, starting point of T, yeah, we have T sequence and a P sequence, all right? Starting point I, starting point 0, yeah, P sequence and a T sequence. Then next one position to the right, I plus 1, 1. I plus 2, 2, and so on, okay? I plus J, here you should also put a J there, okay? With the same pace. Both sequences should move position from left to right with the same pace. How about that? Comac, how about that? In that kind of understanding. All right, yeah, okay, good. All right, yeah, all right. So try several ways to explain this one, yeah. All right, don't worry, just ask the question. Although we use a little more time, yeah, but don't worry, we can make adjustment. All right. All right, yeah, so let's go back to the previous place where we make this guess, n minus m, and we only like to make it close guess. Okay, close guess. Not necessarily accurate guess. Right? Yeah. For an accurate guess, one, you must be very lucky. Second, you must be very smart. All right? Yeah, but most of us may not be that lucky or may not be that smart. We just try our best to make a close guess. So here, this is a close guess, okay? But remember, we have a verified step. If we have a verified step, we can fix the gap, possible gap between this guess and the true answer. Yeah. All right, so we will see that. Yeah. All right, so what's that? All right, yeah, here. How to fix that gap? Yeah, here, let us do testing. here. Think about, there is an extremal case when the given text has the same length as the pattern. How about that? Is that allowed? The number of characters in the given text equals the number of characters in the pattern. Is that special case allowed? Yes, it is allowed, right? Yeah, it's a legal case, right? Yeah. If it is a legal case, but it is an extremal case, we can use it. Usually, when we do experiments, we like to use extremal case. Yeah, so use an extremal case for testing. Okay, now here we use an extremal case for our experiment. If m equals m, then the answer, look at the answer. We have one substring that could be matched against the given pattern, right? Yeah, the same length. At least we can do one string comparison, right? Yeah, that the answer should be 1. All right, yeah. Then let's look at the difference. M minus n, this guess equals 0. And here the answer is 1. Our guess is 0. There is one difference. How about that? That one difference, that is the gap between our guess and the true answer. And that gap, we need to fix it. We need to make an adjustment to remove that gap. All right, now I think you have a chance to do one adjustment to make your guess right. How can you do it? Hey, how can you do it? Yeah, all right. Here, yeah, I need to erase this part. To do it, your answer is n minus m plus 1 after our final fix. How about that? How about that? This is the so-called guess and verify strategy. Right? All right. So you will see it's pretty effective. Yeah. And then later, we will have many situations we need to use this simple and effective strategy. Yeah. All right. Yeah. Next, let me do the second half, implementation details. We need to use a diagram to find the answer. All right. The first m substring, yeah, visually, yeah, that is the first m substring we need to consider. M consecutive characters in the text sequence. All right. Then the location of the first m substring, I equals 1, because the leftmost position of the substring, m substring. Yeah. All right. Now we also would like to look at the last m substring. Last m substring in this sequence. Yeah. But the last subsequence, it is not quite clear what is the subscript of the starting point, T location. The first character in the last m substring, what is that position? It's not clear, right? It's not quite clear. At least we need to do some computation here. Yeah. But the question is, how do we find exact location of this question mark? Okay, yeah, here we need to apply some technique. Yeah, all right. So I like to introduce a technique to find this unknown subscript. Yeah. All right. Here we use a very important idea in math problem solving. Yeah, actually, math is a place that this idea is commonly used. Yeah, but definitely we can use it in many other places. Yeah, it's called invariant idea. Invariant idea or method, yeah, or view, yeah, whatever. But the key word is this invariant. What is invariant? What is invariant, right? Yeah. From this word, you may think of many different things, but here, let me just describe it a little bit. Invariant, we talk about some property. Okay, the property that does not change when they consider all different cases. All right, that is the general description. For our current example, let me use invariant to describe our current situation. Yeah. Look at our situation. We move our M substring from left to right with consecutive locations, right? From I equals 0, next one I equals 1, third one I equals 2, and so on, in consecutive positions. Yeah. When we move our substring, we need to find some special property that never changes. When we move a substring, many things change, right? Yeah. The location of each character in the M substring, they all change. Many things change, but here we need to find some critical property that never changes. That property, if we can catch it, if we can discover it, then we can take advantage of that invariant. Yeah. That property never changes, that means invariant. So we just use that invariant property, then we can figure out, a lot of useful information. That is the idea. That is the approach. Yeah. All right, so here, let me show you how to apply this idea to solve this subproblem. Yeah, this is a little small subproblem in the original given problem. Yeah. All right, so the difference, look at this property. The difference of two end subscripts of each substring, yeah, of each M substring, yeah, precisely each M dash substring. Look at that difference. When you move, yeah, so a lot of things moving to the right, but when you look at the difference of the last character in the M substring and the first character in the M substring, take that difference. That property never changes, right? That property never changes because that difference for all your M substrings, they are exactly the same number. Can you imagine that? Yeah. Yeah. Any question? Understand that property? Any question? Understand this property? Yeah. Let me use another way to explain it. Yeah, another way. Yeah, to help you understand this property. All right. Look at, yeah, let me just use the first M substring. Look at the location of the first character in the first M substring, T0, 0. The last location, Tm minus 1, that's M minus 1. All right. Now, when you increase T0, the 0 by 1, that means you move one position to the right, the substring, M substring. You also increase M minus 1 by 1, right? So that is the number of the number of steps you increase for T0, that same number you also add it up to the last subscript, n-1. How about that? Okay, every time you increase T0 at a subscript by 1, you also increase T sub n-1 at a subscript by 1. How about that? By 2, the first one by 2, the last one also by 2. How about that? The first one by 3, the last one also by 3. But when you take the difference, those 1, 2, 3 all cancel out. How about that? All cancel out. So the difference is the same. All right? Yeah, that kind of observation. Yeah, you need to have that kind of observation. Then you will get stronger in your problem solving skills. Okay? Yeah. All right. Based on this property, we can set up an equation. Yeah. Because for the first m substrate, the difference is n-1. Yeah. But what is the last substrate? That question mark, we use x to represent it. Okay? We use variable x, unknown variable x, to represent it. Then we look at the difference of those two subscripts, n-1 minus x. And these two expressions must be the same. So we get a linear equation with respect to variable x, right? After simplification, x equals n-1. So we find the value for that little question mark, that x should be equal to n-1. All right, so we find the answer. All right, yeah. Think about this procedure. Although it's a simple example, but the idea is important. Invariant idea, this one is important. And in our later, we will have several questions. We need to use the same idea. Yeah, just keep in your mind. Later, we need to bring it up and apply it several times. Invariant idea or invariant approach. Yeah. Okay. All right. Then the final answer. Yeah, we have to start quickly. We use too much time. Yeah. All right. Yeah. The best case efficiency. Yeah. The first m substring, we can find the answer, right? Yeah. But here the m. Yeah. Here I put the answer m. Yeah. So I like to write explicitly. Yeah. Best case efficiency, when we take the first m substring, we get a match. That's the best case. So we do one string comparison. One string comparison. But we do m character comparison. How about that? Okay. Comparison. All right, yeah. M character comparison, one string comparison. Here, M refers to the character comparison, not string comparison. All right. Worst case, we need to go through all the possible M strings. What is the number from 0 to n minus 1? Right? N minus n. N minus n. Yeah. How many? That many possible substrate. Yeah. Remember, that's our answer, right? Look at that. In the previous slide, we just calculate using guess and verify approach. We find this answer, parenthesis, n minus n plus 1. That number of m substrings, but for each m substring, we need to do m character comparisons. So the total number of character comparisons, m times parenthesis n minus n plus 1 as the worst case. Yeah. All right. Then the average case efficiency. Here it's pretty easy. Yeah. because, incremental in the, yeah. So you can see the average, just the first one plus last one divided by 2. Yeah. All right. Although you can use the way you add up the number of character comparisons from the first one through the last one, then you take that division. After simplification, you also get the same expression. Yeah. So here I do not go through that details. Yeah. So you can do the work on your scratch paper. Yeah. All right. So here we complete this topic. Yeah. All right. So yeah, I pretty much double my planned time. Yeah, because so many things to explain. Yeah. Although at the beginning, I feel this is a easy question, so I do not need to explain that much. But during the explanation, it looks like I need to do a lot more work. Yeah. Anyway, yeah, we completed. Yeah. All right. Any question so far? Yeah. On the understanding? Yeah. All right. Then I will move to a new topic. All right. Module 3 topic. So let me get out of this presentation first and bring up next. Yeah. New. Yeah. Module 3 presentation. All right. All right. Yeah. So the first page. All right. Module 3, recursive algorithms. Yeah. I think most of you heard of, and actually you have experience use recursive algorithms. But in this module, we will study in a deep way. Yeah. Yeah. Try to study, in more details. Yeah. Part A, Introduction to Recursive Algorithms. And 8.1, the first view of recursive algorithms. Let's look at the recursive thinking. Now, so people use recursive thinking to solve real-world problems. And here we mean the computing problems. Yeah. All right. The question, why recursive thinking is important in problem solving? We try to understand this question. Okay. Yeah. Yeah. We are used to straightforward, non-recursive thinking in problem solving. Yeah. Based on our intuition, we feel comfortable using the straightforward way. Yeah. But using the recursive way, we need to get some training. We need to learn this method with some effort, yeah, with some abstraction effort. All right, yeah. And we try to adapt our thinking to this new way. This new way, at least for myself, I just look at my own experience. The first time when I saw the recursive algorithm, it took me quite some time to understand, how can you do that, right? How can you solve problems using the recursive way? A function calls itself. Can you do that? A function calls itself. How can you do that? All right. Yep, because that kind of recursive way, based on our real life experience, many times you cannot do it that way, right? Yeah. Think about that, because based on our intuition in real life, think about if there is a situation that A statement relies on B statement, B statement relies on C statement, C statement relies on A statement. Can you make the whole thing work, right? Yeah. Because if we try to connect to this situation, you know. Yeah. How can one thing refers to itself, right? Yeah. So that at the first time, that will cause some problem. Yeah. All right. But in our computer programming, so here we're talking about computer programming. Computer programming. Okay. Yeah. Okay. It's different from our usual everyday life experience. Computer programming, if those programming language designers, if they can make recursive function call, that feature happen, then we can use it, right? Think about it this way. If the programming language designers, if they can make our programming language support recursive function call feature, then we have no problem, right? Yeah. So that's the key point. Yeah. And then later I will explain a little bit, in general. So not in a lot of details, just in general idea, how to make recursive function call happen in computer programming a little bit. Yeah. All right. So here, yes, we can do it. Yeah, because the high-level programming language support this feature. Yeah, make it work. So we can use this feature. Yeah. If people go back to the history of programming language, yeah, for the early high-level programming language, they did not support recursive function call. Because at that time, those designers, they didn't know how to do it. Okay, that's why those programs did not support. So we as programmers, we cannot use. If people use the very old version, high-level programming language, they cannot do recursive function call. But in our modern and advanced programming languages, yeah, all high-level programming languages in our modern time support this basic feature. Yeah, it is a basic feature, yeah, not some fancy, advanced feature. Yeah. All right. Yeah. Some problems can be solved in both ways, non-recursive way and a recursive way. Yeah. There are two ways we as programmers, we can take to solve computing problems. Yeah. Yeah. All right, so then we can do comparison. Later, yeah, below, yeah, in my second half of the slide, I will do comparison of these two methods. All right, next one, power of recursion. Yeah, that's the reason we consider recursion. Power of recursion, it is very powerful. Why? For programmers, recursive thinking is really important problem-solving option. Yeah, let me say option, because it is so powerful, extremely powerful. So we cannot do our job without it. Yeah. We have to put this powerful tool in our toolbox. Yeah, I mentioned that toolbox idea, right? Problem-solving toolbox. We build up our problem-solving toolbox, and this recursion method, that is a powerful toolbox, a tool. We drop it, we put it in our toolbox. Yeah. All right. Yeah. And here, some relatively hard problems can only, I put a parenthesis, only be solved by recursion. Yeah. here, if you some of you read a textbook, yeah, because the reason I put only, because in a textbook there is one sentence. It says every time when you can use the recursive algorithm to solve a computing problem, you can also use a non-recursive algorithm to solve that problem. Okay, yeah, or similar sentence, may not be exact. I just give you the basic meaning, yeah. But that, based on my real world experience, yeah, that could be very hard. That could be very hard. Yeah, even most people do not even consider non-recursive solution for some relatively hard computing problems. Yeah, so we will see one later soon. Yeah, all right. Okay, yeah, so let's move to the comparison here. Iterative method versus recursive method. Yeah, all right, the basic comparison. For iterative method, yeah, non-recursive, yeah, that usually iterative. Yeah, all right. It uses less resource, but harder implementation. Yeah. For some special computing problems, if you want to use iterative way, that is extremely hard. Yeah. Many times you may not be able to do that way. Yeah. Recursive, you need to use more resource. You need to use more resource. But implementation side, easier. Here you can see some kind of trade-off, right? Yeah. You sacrifice a little bit here, but you gain something there, things like that. Here, you spend a little more resource, but as the gain side, you make your implementation easier. That's the main point. Yeah. All right. Yeah, but I may like to explain a little more why you said recursive way use a little more resource. Yeah. So that is related to the internal recursion implementation inside computer memory. Okay. In main memory. Okay. Computer main memory. The basic idea to implement recursion is using the data structure, stack data structure. Okay, yeah. I think you have learned it in CS3250. Stacks data structure. It is a pretty simple data structure, right? But here you can see recursion feature relies on this stack data structure. All right. Because think about here, I just use the general description here. For example, when you make a function call for m, yeah, look at that. Our goal, yeah, so here, when we start, our goal, we want to find the function value f of n, okay? But the f of n relies on f of n minus 1. F of n minus 1 rely on f of n minus 2 and so on. Okay. So when you try to get a value of f of n, it's not available. Okay. If it is not available, you push it into the stack f of n at the bottom. All right. It relies on f of n minus 1. So you need to find f of n minus 1 first. But f of n minus 1 is still not available. So you push it into the stack, next level, sorry, f of n minus 2. Yeah, oh, sorry, n minus 1, and so on. So then f of n minus 2, still not available, you push into the stack, all right? Yeah, then, so you make your stack deeper and deeper, and at the end, you reach the top of the stack, f of 1, and this value usually it is given. Okay. When top of the stack, the value is given, you have the top function value, then you can use it to find second in the stack, third in the stack, and so on, all the way down. Finally, you reach the bottom, then you find the final answer of f of n. That's the basic implementation idea inside that stack for recursion feature in high-level programming language. In that way, to maintain a stack, because you can make your stack very deep, right? Deep stack use a lot of resource. Okay? A lot of resource. So here you can see nothing is free. Recursion feature in high-level programming language, it is not free, right? The cost, you need to pay this cost, okay? People need to pay this cost, right? Pay this cost. Then your gain, you make your solution easier, okay? You solve a relatively complicated solution in an easier way. How about that? That's the, key property of recursion. Okay, recursion. Yeah. The good side and the bad side, the positive side and the negative side. All right. Nothing is free. Recursion is not free. Yeah. It has a, quite some cost. Yeah, quite some cost, but we are willing to pay that, right? Yeah, we are willing to pay that. Yeah, people, programmers, they are willing to pay this cost. All right, okay. Yeah, I mean, the negative side for this class, we pretty much reached the end of this class. Yeah, let me just use a few more minutes to describe the next question, factorial question. That's pretty simple. Calculate the factorial. It's a simple question, but I like to use this simple computing problem to introduce, as a simple introduction to recursion. All right. So the problem, given non-negative integer n, find the factorial value, number, function value. Yeah. So this is used as introduction, yeah, simple introduction for this big topic, recursive algorithm, this big topic. Yeah. Let me just use 5 minutes to get you started. And the next time we complete it. Yeah. Method number one, here I like to use two methods. Yeah. Method one, iterative method. Yeah. Very easy, straightforward. Yeah. First, we know the definition of factorial. N factorial defines in this way. We start from 1, then we do multiplication on the consecutive integers 2, 3 through n, the last one, n. Yeah. That is the definition of the factorial. Yeah. All right. But because look at the given question, we look at a non-negative integer, because non-negative integer including 0 case, right? Including the case n equals 0. When n equals 0, we also need to consider factorial, right? But here we define 0 factorial as 1. Is there any problem? 0 factorial equals 1. Yeah. Based on intuition, yeah. Just think about, use your intuition. Can anyone get a reasonable explanation on this assumption? Yeah, we can call this assumption, but you cannot make arbitrary assumption, right? your assumption must be reasonable, right? Yeah, you cannot make arbitrary, your assumption must be reasonable. Okay, what do you mean reasonable? Not causing any contradiction. Okay, reasonable here means no contradiction. In future. Okay, that is the right way. If you make some absurd assumption, think about, you make 0 factorial equals 100. Can you make that? 0 factorial equals 100. That's ridiculous. Okay, that's absurd. No reason to do that. Because if you make that assumption, sooner or later, you will get a huge contradiction. That's not allowed. All right? Yeah. But the good thing is, if we make this assumption, 0 factorial equals 1, then we will have, good life later in future, because we will never have any contradiction when we use this factorial definition. All right. But how to see it, right? The question is how to see it. How to see it, okay? Yeah. Yeah. We will see it. Yeah. Later, yeah, I will explain why it makes sense. Yeah. Why we won't have any contradiction in the future. Yeah. All right. Yeah, we run out of time. Yeah. I have to stop here. And I couldn't complete my plan big time because I just get started my second topic, and I still have most part of this part A left. Yeah, so that dragged down our plan, quite a lot. Yeah, but I will catch up slowly. Okay, yeah, I will, try to catch up using the remaining of our module 3, part A, B, C, D to catch up. How about that? Yeah, so I try my best. All right, so let's stop here, and I will post the video, as soon as possible. Yeah, sometime today. Yeah. All right, so that's it. Have a good evening.